So welcome everybody. We are very pleased to be able to hold our Atto Fridays today. For the people who are logging in from America, we apologize for the time, but if you have very distinguished people talking, you know how it is. They're busy, we are all traveling, and actually today he is logging in from Prague. So our speaker today is Professor Merdji. We are thankful that he accepted the invitation to speak. And he is, in fact, now in Ecole Polytechnique. He is the director of research there. And that's the place where he did his PhD. So he did a PhD on X-ray absorption spectroscopy in laser plasma fusion in 1998. Then he started a postdoc in the group of Bertrand Carré at CA Saclay, joined the group afterwards as an associate researcher to collaborate with Pascal Salière in pioneering attosecond pulse generation and characterization in atoms and molecules, evidencing the Atto chirp in 2003, and molecular quantum interference in the attosecond phase of the harmonic emission of N2 in 2007. And from 2007 to 2009, he was a visiting physicist at Stanford, invited by Phil Buxbaum to contribute to the Ultra-Fast Pulse Institute and Free Electron Laser Attosecond Science. And once he went back to France, he created the Ultra-Fast Nanophotonics group and brought contributions in lensless imaging approaches using unconventional sources of light, from partial coherence to attosecond broadband time structure. In 2020, he has opened a new lab facility, Nanolight, dedicated to high harmonic generation in semiconductors, with a specific emphasis on light-matter interaction at a nanoscale for the generation of beams carrying spin or orbital angular momentum and nanoscale imaging of transient processes. And in March 2022, he moved back to Ecole Polytechnique, as I said at the very beginning, so 24 years after his PhD, back to the origins. And from one shot every 2 hours in 1998 to 20 million shots per second in 2022. So we have made some progress here. And we are really, really pleased he accepted to speak today. And his interest is now to study entanglement in high harmonic generation to explore new quantum diffractive imaging schemes. So how quantum is Atto is the question, as we all know, and we're addressing this as well. And today he'll talk about high harmonic generation from classical to quantum diffractive imaging. So the floor is yours. Feel free to start. We're ready to listen. And thank you all for joining.
Thank you, Carla. Thank you for the invitation. It's fantastic to be there to share some of my work on this Atto Friday quantum battle. We're going to see on the very end what we're going to face with quantum imaging stuff, but I'm mostly going to talk about classical imaging, which is already very difficult and challenging. So I'm very happy to be here. So I would like also to thank all the organizers, Sophia, Didis, and Thomas, for the support behind the scene. There are a lot of support. So, so with this, I think I can start to share my screen and go ahead. So, and it's a full stream, and the questions are in the end, and that's the format, I guess. Yeah.
We typically have the questions in the end because it's easier for us to edit and people can put these. And we have also some people on YouTube. Hello, people from YouTube. There are quite a few of you today. And we're ready to go. So questions in the end, and we're going to have bonus material. So to watch live and support the speaker, okay. Right? So we're ready to go.
Thank you. So hello, everybody. Hello, people from the south, the north, east, west. So in this channel. So I'm going to talk about harmonic generation. So I spent like 20 years working on that, but more recently, I went into diffractive imaging, classical imaging. I'm going to show you what are the challenges, how it is interesting, how you can get information from the object. And then I will move to quantum imaging, which is kind of magic stuff, but I will explain that it's not so magic, it's physical. I would like first to, let me go on this. Yeah, I would like to thank so my past group when I was at CA, so Willem Boutu, who made a lot of contribution in this in the topic I will show. Also David Gauthier, who was my first PhD student working on the topic, and now he got a senior position at CA Saclay. So congrats for him. And this is the whole team. So a lot of them already moved because this picture is from 2018. So let's move forward. I would like to thank also very specifically Bertrand Carré, who is not with us anymore, but he accepted me in his group in '98, so a long time ago. And he supported me to build my group and so on. And Pascal Salière also, who we had very nice discussion about attosecond science, and then I moved a bit to my field on imaging. I would like to thank also Phil Buxbaum, who invited me at Stanford, and he was kind of a mentor before I started my group. And then on harmonic generation in imaging, I would like to thank Milutin Kovachev and Marta Pajardo and Jens Bigger, who are my collaborators for more than 10 years. And on the current diffractive imaging, Janos Hajtu, who was also mentoring me in this field, and Henry Chapman. And I like this picture of Janos, you know, he's doing imaging, and I like this kind of free perspective of himself. So, and it's about the story of an image, you know. What I would like first to emphasize is really this thing about what do we see, what is an image, how an image is built. Can we really believe what we see? Is this real? Is it fake? How the image is assembled? Because you can have images from X-rays, from visible light, from electrons, from different sources of light, different protocols. So can we really believe what we see? So this is, I like this, to put this perspective of the story of an image. And for example, this image, when you see it at the first sight, it looks real. And this penguin flying on the island, it's just a fake, and it has been just sent by the BBC. It was just to show that how people can be influenced by fake images. So you can produce whatever image. Here it is with Photoshop, but you can produce fake image also by capturing the camera with some filters. Another example, during the coronavirus crisis. So these are, we love the news, this outbreak news and Fox News and blah, blah, blah. But what we see here is those picture of the coronavirus behind. It looks very spectacular and a bit scary too. And is it real? These are totally fake images. Like this coronavirus look like a trumpet stuff. So how can we really get good images? These are real images of the coronavirus. This is for sure that television will not show such picture, but because it's not fancy and sexy at all. Now, if you add some false color, this looks like that, it's a bit better, but these are real images taken with cryo electron microscopy, the real first images of the coronavirus. So let's move forward about how an image can be built. And if you want to go deeper, you can have, like, for example, this case of X-ray visions. These are two doctors that are struggling how my patient has a fragment of a glass fragment into his brain, but we cannot operate with our current technology. And Superman came and said, oh, but I have an X-ray vision that is much powerful than your hospital X-rays. And he shined the brain, and you can see the fragment of glass, and the doctor are ready to operate. So, and this is really a lens X-ray vision. You have no lenses, no camera, just the eyes shine. So, and how we can create images without lenses. So this is an example of a diffraction pattern. I will show you later on a little game. We will play a little game with this picture, and you will have to guess what is behind, how the image is formed out of this diffraction pattern. So first of all, the motivation, why we want to look at smaller things and faster. So it comes from really observing fast processes. So it's from the 50s, 60s, they invented flash imaging with microsecond lamps. So where you can really capture this moment, this fraction of a second. Now, transistors are operating on much faster time scale. So this is microsecond, nanosecond, picosecond. Then you need terahertz imaging or other techniques. And if you want to look at ultra-fast optoelectronic system, you will need femtosecond down to attosecond light. But together with that, to resolve those features, you will need short wavelength. So if you are at the scale of a cell, what you would need is a micrometer or maybe about millimeter. But micrometer wavelength will resolve this kind of cells. And then if you want to go to atomic scale, you will need nanometer or sub-nanometer wavelength to record that. With electron, you can reach those wavelength or X-rays. So my motivation is really to move to attosecond imaging. So I'm trying to move this stuff. Okay. So basically, so it doesn't move, sorry. Okay. So our world is surrounded by exciting phenomena occurring on attosecond and time scale and nanometer space scale. I can give you like 2 examples. These are quite scientific examples, but they really prepare future technology, future science, and answer future concern for our society, just like ultra-fast electronics. If you want to probe electronics that go millions times faster than current technology, you will need really to get attosecond nanometer probe. So if you have, for example, this kind of device, which is not yet an optoelectronic device, but it's still on the research, you have electrodes, and you see that with an electromagnetic light, so this is here in red, and you can produce a current so this is time scale that occurs transiently on few hundred attosecond or a femtosecond mostly. And so you would like to resolve that in space and time to optimize future petahertz electronic devices. Now, if you look at biology, energy transfer is very important. This is an experiment from Francesca Caligari, where they look at the whole migration in a large molecule. And it's very interesting how they did it. But what we would like to do is to create images of this energy transfer to really reach the real space and time scale of this energy transfer. And you see this molecule will arrange itself, and this is very important for energy transfer in the photosynthesis, but also for the vision. All of the molecular vision and will work on this kind of concept of charge migration. So you want to resolve processes on ultra-fast time scale and very small scale. So this is the spectrum, so infrared. So you need really X-ray that are produced on extremely short pulse duration. So let me go forward. I have just some. Okay, so this has motivated the construction of billion-dollar facilities. So I draw here some example, the LCLS at Stanford. So I was there actually in 2009 for the first experimental beam time at the AMO with Phil Buxbaum. We did the very first experiment at the LCLS. I was in 2006 at the VUV-FEL in Hamburg, but this is the XFEL that I've opened a few years later after the LCLS, and you have the PAL at Korea. So these are really huge facilities. This accelerator is 3 kilometers long. So you can imagine that to produce this short burst of attosecond light, you really need this big machine. But there are alternatives. So I draw again this space and time scale. So picosecond, femtosecond, attosecond, and here down to the nanometer. So those XFEL can produce femtosecond and even attosecond pulses. They are big machines. And now if you use a laser, femtosecond laser, you are already in this femtosecond time scale, but the wavelength is in the visible or in the higher or even in the mid-higher. So you cannot resolve really a very small object of nanometer size. What you need for that is to down convert the radiation through a process called harmonic generation, where you generate harmonics. so of this wavelength at much shorter wavelength than basically they stand in the XUV range. And you can see here when this big laser is focused, so there is a gas jet, there is a tiny light here, and it's a millimeter or 100 micron size. And so that those X-rays are produced on a very small area, and it's a much more compact than XFERs. So I found out an old slide from 20 years ago, and I love it actually. So I display it again. So this is the gas jet. So you have your laser, you shine your laser on this target. So you create a strong field interaction. So I will not go into the detail because you have a lot of Atto Friday and Quantum Battle that explain deeply what is the harmonic generation process. So I recommend you to go on this channel of the Atto Friday channel. So you generate harmonics, you have a grating to analyze. This is the spectrum recorded by Pascal Salier. So it's kind of a historical to show it again because it was recorded more than 20 years ago. And it is still extremely timely, and it is really useful. You see a lot of noise. This is all detectors, and this is a spectra that I recorded at CA, I think it was in 1999, and it's really nicely contrasted. And you see the plateau, the cutoff, and harmonics, what are emitted in this sub 100 nanometer wavelength. So you can see here 13 nanometer is the wavelength chosen for the UV lithography. But harmonics are also generated at shorter wavelength here, like few nanometer wavelength. So basically, you can reach the Water window, and this Water window is important for biological imaging. So I would like now to talk about diffraction of light. So because this is basically what we're going to use to have our X-ray vision. So I have here a few examples of what diffraction does. This is what you would see if you look through a window without any curtain. So you see those spots of light in the mountain, in the valley. And now if you close the curtain, I will not do it here because it might be a drama, but you see some diffraction. You don't see any more individual spot, but you see diffraction from the curtain. So it's interesting to notice that this phenomena occurs also on different surfaces, like here on a CD or on a TV, but also in nature, like the wave of the ocean can be diffracted through a hole here in a wall, and you see here a nice diffraction pattern from the wave of the ocean. So, and now I will show you that this diffraction carries some important information about the object where the light is going through. So this is, for example, the object, could be whatever. And we have a plane wave that comes, and what will happen is that each point from the diffracted surface behaves like an individual emitter. So that in the far field, you collect the interference from all these individual emitters. And this is what builds radiation in the far field. So it resembles again to this diffraction of waves from the ocean through a pore. So now let's consider two cases. One case is when your aperture is much larger than the wavelength, okay? And then the other case is when your aperture has a similar size as the wavelength. What will happen to your radiation? If you have this case, you will not be too much affected, and you will get kind of a shadow of your object, so like this. But if the aperture is much smaller, it will diffract like this. You can have spherical wave of diffraction. And importantly, this spherical wave contains information about the size of this aperture. So if the aperture is large, you will get small diffraction pattern. And then if you squeeze the hole, you will get a large diffraction pattern. So, and this is already a spatial information. So I will tell you how those two spaces, so this is the object spaces, and this is the diffraction, so the far field, are how they are connected. So I would like also to illustrate through Young slits, so the interference between two holes, two sub sources that interfere in the far field. They will interfere and it will produce either constructive or destructive interference, so destructive here, blank, or constructive, depending on the coherence of the source. And the interfringe of this diffraction pattern will depend on the slit properties and the wavelength, of course, of the radiation. So, and in fact, the analog, if you want some representation of what happens in the real space, so when you see an object, if you observe the diffraction pattern, and in fact, it's nothing than the Fourier transform, so what call that you obtain through the direct Fourier transform. And if you want to go back to the real space, you just do an inverse Fourier transform. I say you just do, but it's not so simple. Now let's look at what happened to the diffraction pattern. If you change our square in different direction, you will see how the diffraction pattern will evolve. So if we squeeze on this side, the diffraction pattern evolve in this direction. If we squeeze on this side, diffraction pattern extend on the vertical direction, and so on and so forth. Now, with this little instruction, you should be experts in analyzing just with your eyes a diffraction pattern and guess what is the object behind. So I would like to propose a little game. I love games. So this is a Fourier game, I call it, due to Fourier. So this is the diffraction pattern that I showed at the beginning. Some of you already know what is the object behind, but so like Superman is just asking, well, what is behind this object? So we already learned that when you have some preferential direction in your diffraction pattern, this is due to some specific object. If you look at this line, in fact, so in the real space, it is due to an object that has this feature. Then the other oblique diffraction line, another object in the space that is oblique. And then you have this vertical diffraction pattern with some modulation. It's not as continuous. If it's not continuous, it means that you have more than one object. So you have 1 and 2 due to the modulation. Okay, now let's try to ensemble them. And what we see, in fact, is the diffraction from this nanoscale Eiffel Tower. This is an electron microscopy image of the object. And this is the diffraction microscopy, the reconstruction from the diffraction pattern. So real space, reciprocal space. So let's continue again. We love to play. This one looks more simple, so you might guess already what it is. So you have, again, a horizontal diffraction with some stripes. So we know already that this is due to 1, but not only to 1, but 2 objects, because you have modulation, like the 2 slits of the Young's 2 slits experiments. Okay, and this oblique line is quite continuous, so it's a single object in this. And then you have circular pattern with some fringes. So these are certainly some holes in the object. Okay, but it doesn't look really like an object. So, and in fact, what is missing here is an important information, because what we record is only the amplitude. We do not record the phase, and the phase will inform you about where those objects are located in space. Whereas the amplitude just give you information about their shape, but not about their position in space. So in fact, the information carried by the phase is important. And this is what the object that you get in the end. You get all the feature, but the phase only can tell you where they are located in the space. So another example, we love to look at famous people. So this is Marilyn Monroe and Wilhelm Conrad Röntgen from X-ray. These are absorption objects, no phase shift, so regular. So let's do another game. So this is the Marilyn Monroe, and then I get the Fourier transform. I get the magnitude of Marilyn and the phase of Marilyn. Okay, let's do the same with Wilhelm. We get the phase of Wilhelm and the magnitude of Wilhelm. So now let's take the magnitude of Marilyn and compute with the phase of Wilhelm. And we do the inverse Fourier transform. Sorry, there is -1 missing. inverse Fourier transform, and what you would get here, and then we do also the same. We take the magnitude of Willem and the phase of Marilyn. And in fact, what you obtain is really kind of magic, or it resembles to some weird situation where you have a superposition of two images, but what dominates, what you see clearly, is that the phase is crucial. What dominates here is the phase. Mainly, you see from the amplitude of Marilyn that the phase of Willem dominates the feature. So now I go into some basics of diffractive imaging. So on top, this is classical imaging. So you have a light source, an object, and usually to form the image, you use a lens and then a detector or just a screen, and you get the image, okay? And now in lens imaging, you do not have any more a lens, which is practical with electrons, X-rays, where lenses, optics are in general very hard to manipulate and to produce, but first to produce. So you have your X-ray laser. So I take a synchrotron here, it could be harmonic generation, whatever the source, coherent. So you have your object, you illuminate, and you directly measure on a 2D detector the diffraction pattern. You measure only the amplitude, and like the Superman vision, if you do not know the phase, you don't know how the object is assembled in the space. So you need a phasing algorithm to retrieve the phase and reconstruct the image. So it's a two-step process. So in this process, so you eliminate your object, record the amplitude of the diffraction pattern, but you don't know the phase. And in fact, at this point, you cannot retrieve the image. You cannot do it. So you have to go through some numerical processes, or you can devise some different application. Either you do a phase retrieval, but I would like just to emphasize that there is another approach called holography. I mean, everybody knows. Which is a deterministic approach, direct deterministic approach, where you shine your object and you superimpose on top of the diffraction pattern the reference beam at the same wavelength, and you have modulation, just like with the fringes of the two slits, and those modulation encode the phase. And then it can be revealed by your Fourier transform process. And there are a lot of different holographical schemes, so I will not go into the details of that. And then this is the lens imaging. They resemble a lot, except that here you do not have, here you have the reference, and here you don't have any reference. You just measure the diffraction pattern. So it's a non-deterministic approach, and you will use algorithm. I'm not going into those details about how the algorithm, but I will talk about the difference map, how it works. So there are some conditions to have this working, and we'll tell you what are the conditions to have this technique really working. So what is nice in current diffractive imaging, it's basically, theoretically, it is only limited by the wavelength and the signal in an experiment. Or the signal and also the size of the detector, of course, because the resolution is given by the large angle. The higher the angle of the diffraction pattern you collect, the smaller the feature you can resolve. So this is really the gymnastic of the Fourier transform. What is large in the real space is small in the reciprocal space. So it's a two-step process. You record the diffraction pattern, and then you recover the object structure numerically using an iterative phase retrieval algorithm. It is sensitive to the phase as well as the absorption of the specimen, but it brings also some difficulty due to that. You can achieve 3D tomographic reconstruction if you do several projection of your diffraction pattern, or you turn your sample, you get a 3D rendering and possibly a reconstruction of on 3D of your sample. But you have to assume some information, and there is a strong difficulty is to recover the phase. I will show you one of those difficulties of the phase retrieval. So just to show you what kind of problem we want to solve. So there are different classifications. So we have a linear problem. So this is the space of solution. So basically, when you have a dip here, the solution will stand in this dip. In a convex problem, it's also here. So the solution will not stagnate over there, but will go in this local minimum. But what we have in phase retrieval is a non-convex problem, so that you have several minima. This is illustrated here. So in a convex optimization, you have a global minimum. So when you try to find a solution, you converge rapidly, but in a non-convex problem, you have many minima. So this is an example with like 4 pixels. So I add also zero padding around. So I'm not going into detail about the zero padding, but let's fix those 2 pixels, row 3 and row 4, and we vary row 1 and row 2. And let's look at all the, we will compute the error that we do systematically. And this is the 2D map of this error. And you see different minima. So it's the same as this one, but in 2D. So you see here in red, 2 red minima, and in blue is the real solution. So you see that the algorithm can really go in that direction in this landscape of non-convex solution. So we have to solve this non-convex problem. So if you want really to have our lens 6 revision, this is a huge problem, okay? So, but we have some help because we are navigating in a space of constraints. And the Fourier space, for example, we measure this diffraction pattern. And we always know that we can go back and forth between the real and reciprocal space, but always we're having the information that the square of the Fourier transform is equal to the measured intensity. This is one constraint. And we have a second constraint that will help the fed retrieval algorithm to converge. We have the support. We know roughly where the object is, because if you Fourier transform this diffraction pattern, you get this kind of picture. So, and then let's put a 0 to 1 mask, and the black area, we are sure that the object is contained in this black area. So it's really restrict the space where the algorithm can go and compute some solution. So we have these 2 constraints. But to have this working, it means that the object has to be isolated in space, okay? So let's go again in this space. Real space is A, blue. So this is our one constraint. Fourier transform the space B. And the solution that we want to find in this non-convex problem is the interaction, the intersection between the 2 spaces, okay? So how are we going to do? Because in the beginning, we have no clue, no idea. So we start from random position in this space, and we will work with projection on either this A space or in the B space, okay? And what the algorithm will do, it will go back and forth between the 2 spaces and hopefully converge to the solution, okay? And this is illustrated right now in real time. So this is the error function and the algorithm that starts. So this is the test object, and this is a diffraction pattern that we have collected and put into our algorithm. So we see that the algorithm converge quite nice, and the error tend to go to the lowest value. So, and I would like to see you that you watch again the movie. So really, it's random in the beginning. This is what I want you to show: random, and then the algorithm constructs iteration after iteration the object. Finally, it really converges because you know that the phase puts the correct information in space. Okay. So, so this slide is just to some recap of the contribution in this field. I mean, the first one was Max von Laue in 1912, who proposed to use X-ray diffraction to visualize a crystalline structure. And in fact, in this, so these are other examples. We have the diffraction that goes around, but you have coherence there. But the coherence is really at the level of a cell of the crystalline cell, but like few atoms. So it means that the extension of the coherence length is quite reduced in this case. So, and then people have trying to solve the phase problem, because if you know the phase, you can really arrange all your atoms in space and reconstruct with high fidelity an object. So these are other contributions, mostly with different algorithm. And then the first demonstration of X-ray crystallography and imaging of non-crystalline sample was performed by the group of John Serre and Gain Mao at UCLA, who achieved this in 1999. And after this was 2 decades of high success, and one of the pioneers is the Henry Chapman, Janos Aitu, and John Spence, and they get granted of the Aminov prizes in crystallography from this Royal Swedish Academy of Science in 2021 for their contribution. So, and it's an important field which has brought a lot of impact, not only in structural science, but also in biology. So this is just to show you the first experimental demonstration of lens-lens coherent diffractive imaging in 1999, where you have this diffraction pattern. By solving the phase, retrieving the phase, we're able to reconstruct this. This is a nanoscale object image with 1.8 nanometer radiation from a synchrotron radiation. So, and then this has been followed by stunning results in biology, like the 2D image of a Mimi virus, or the 3D rendering and imaging of a human chromosome. Also in semiconductor technology, there are nanoparticles, also nanoplasma, when you want to look at ultra-fast processes in, let's say, for example, in fusion plasma technology. This is very useful to look at this kind of processes. So now what we want to do is to combine this technique with real-time perception. We want to watch movie at the nanometer scale. We want to watch movie that evolve on femtosecond or even attosecond time scale. So this is, again, an example of, this is a holographic scheme, but whatever. You have here the hologram that reveal an image of a nanoscale magnetic domain. So you can see here with the color scale, so domains of spin up and spin down in the magnetic structure. So it's a static image. Now, what we did, so this was an experiment done at LOA with the group of Philippe Zetoun at this time in 2012, and Jan Luning also in Paris. So you have, again, the structure of spin up and spin down, and we look at the scattering. And with another pulse, we shine with a laser and we look at the demagnetization. And rapidly, if you disorganize these stripes, you will lose the signal and see the demagnetization. But what you want to do is to combine the two of them, the time resolution, space resolution. So it has come slowly, and this is a very nice experiment that has been performed at Fermi, at deep hole beamline. This is a magnetic sample, your soft X-ray at 20 nanometer, a laser that will heat and change the magnetization locally. And they've been able, so it's a picosecond time scale, so from unpumped, so 0.6 picosecond and 1 picosecond. And you see here in this area where the laser is focused that you have a loss of contrast of the magnetic domain. So it's really a real-time measurement of nanoscale magnetic domain over picosecond demagnetization, sorry. So another example is provided here. You have basically here the observation of the melting of nanoparticle. So you have your X-rays and a polarized laser, strongly polarized, and they want to observe the diffraction pattern if there is a link between the laser polarization and this direction and the expansion of the plasma. So, and this is what they observe so far. Sorry, just getting slow in there. Okay, yeah, we get it. So these are the diffraction pattern, and we see this expansion on this side means that the explosion of the nanoparticle has a preferential direction. So this is the electric field of the laser, and they are able to reconstruct some shape of the nanoparticle that is melted and explode in a preferential direction with the laser polarization. So it's fantastic how you can probe matter at a nanoscale. Here again, it's on picosecond time scale. So it's very hard to go on this femtosecond and even attosecond time scale with this technique. And this is what we want to do. So this is the dream experiment. It's a paper. I discussed a bit with Misha Ivanov about this paper. it's a proposition to look at the superposition of states when you have a hydrogen atom and you shine with a laser, you have the superposition of state which induce some attosecond motion of the electronic cloud. And if you look at the diffraction pattern, you should be able to resolve the superposition of state spatially. People are doing it spectroscopically, it's quite advanced, but if you want to have a real image of that, how you can do, you need attosecond nanoscale imaging. And another example that I showed you at the beginning is to resolve attosecond electronics for future petahertz or electronics. And oh yeah, this is running. I have like 2 projects running. They are now at CA with Willem Boutu Petacon project and Optologic project, where we try to produce the first petahertz switch. And here this concern some topological material where we want to switch with the topological system some information on ultrafast time scale. So let's enter into this attosecond world, but spectroscopically, and look at the bandwidth of attosecond pulses. So these are the pulse duration as a function of the photon energy. So let's say you want 100 attosecond pulse. So and with a photon energy about a few hundred eV, which are about standard attosecond sources that exist nowadays. So you are in this region. So with a bandwidth about 10%, 100%. So if you look at optical books, all the equations are written mostly for monochromatic radiation. So imaging protocols are mainly done for monochromatic wavelength. So basically in this area. So, but there are some tolerances. So like the phase retrieval algorithm will tolerate something like 0.1 or 1% bandwidth. So we've been successful in proceeding phase retrieval in this area where the bandwidth is still reasonable. But there is no man's land and nobody did it. So let's look at the broadband spectra. So this is a courtesy of Jens Bigert. So it's a spectra from harmonic generation in the water window that I explained before. So if you want to measure a diffraction pattern and from this object, so the source produces 10 to the 8 photon per second. So with a diffraction efficiency of 10 to minus 5, 6, to get with the full spectrum a correct measurement, you will need 3 hours to get an image. It's still okay. But now, if I want just to use a monochromatic wavelength, you will need a multi-layer mirror or whatever optics. This is a multi-layer mirror. You have orders of magnitude less signal. So it's really dramatic, but it is monochromatic. Then with the signal that you will use from this kind of optics, you will need 2 weeks to get your image. So it's kind of a prohibitive. I remember I presented this 2 years ago before the COVID, and Ken Schaefer, he's a theoretician. He said, a day is okay. So, but not 2 weeks. So we have to find tricks and make use of all the photons and not monochromatically constrained by this mirror. So I will present you what we decided to in the deduction we have taken. So this is a broadband plane wave. So this is an object. It looks like it resembles like a chromosome. Your light or plane wave goes there, and it is diffracted. And each color produces a diffraction pattern. I just put discrete color for this so that you can understand that each color will produce a diffraction pattern, which is a homothetic increase with the wavelength. And in the end, what you measure in your detector is the incoherent sum of all of this diffraction pattern at each wavelength. So I just said incoherent sum, and we want to do coherent phase retrieval. So obviously, you cannot achieve a phase retrieval if you have incoherence that dominates the diffraction pattern. So the trick is to the trick is to be able to monochromatize this diffraction pattern. Again, I have here the stack of different diffraction pattern at different wavelength. what you can do is to take this diffraction pattern and consider it as a matrix. So you project it into a matrix. And if you're able to invert this matrix, you can find a way to monochromatize along this along the diagonal line of this matrix. But it's extremely difficult. And if you try to invert such a matrix with such a diffraction pattern that has a lot of zeros, you get an awful noise, and it's really impossible to invert it. There are some mathematical tricks, and at this time, my PhD student, Julius Huth, found a mathematical trick where you project this, this matrix onto a Krylov subspace. So this is how it works. I recommend you to go there to know how it works mathematically. And this is and this trick works, but the problem is semi-convergent. And because it's ill-conditioned. So you start here. So this is our M0. This is the diffraction pattern, incurrent diffraction pattern, broadband. And what you want to do is to go to the exact solution along this line. But you don't know when to stop, because if you go there, you're lost. So I will show you what the algorithm, is doing. So yeah, should be there. So the algorithm will compute all along and try to stop exactly at this solution. But the problem is that it's diverging extremely fast. So what we try to do is to control it experimentally. So this is the experimental setup to a testbed experiment where we produce a white light broadband, and we have so this is the white light that is generated as a test. And this is the narrow case. And this is the friendly test sample that we're going to use. So I will start first with this narrow band structure and look at, so this is the monochromatic diffraction pattern. And we will look at the reconstruction. It should basically work. Yes, okay. So the algorithm starts with the noise, and you see that at certain point it converges, and you see a nice reconstruction of the object after a few tens of iteration. It's really solidly working with this narrow broadband. I say monochromatic, but it's narrow broadband. It's like 1% bandwidth. So now let's look at the case with a broadband. So we were at 1.2%. Let's go to 11%. So let's compute that. We send this diffraction pattern with the incurrent sum. And okay, the algorithm is trying to find a solution. We see some feature, but it fails. It doesn't work. So again, I go back to the story about fake images. If you think you did the job, you have not done the job, because the image is not, does not have a high fidelity, and it's totally fake if you want to consider that it's the real object. So now let's go to the next step. We take the same diffraction pattern, but we apply our monochromatization. Okay, so this is the monochromatization. We stop at K20. So we recover some modulation, and let's feed now the phase retrieval algorithm. And it works. It's kind of magic, but it is not. It's really conditioned by numerical constraints and experimental arrangements. Okay, so we did some other experiments. So just an illustration with a phase mask in lithography. So this is the broadband pattern. Okay, so we monochromatize again, and we look how solid is the technique as a function of the bandwidth. So ideal case, it is what you reconstruct. And you see that if you increase the bandwidth, the monochromatization works pretty well at 10%, 20% is okay. But if you go up to 40% bandwidth, you see that the feature of the object tend to be smeared out, okay? So And then we demonstrated that Soleil synchrotron also experimentally, but I'm not showing all the data as time is constrained. Okay, so I would like now to show you with harmonic generation also that we were able also to tackle some 3D perception. So again, it's about fake images. So if you are in 3D space, I mean, we are all in 3D space. So now if the world would have been 2D, it's okay, but it's 3D. Like if you have a cylinder like here, if you would look at this object from this direction, it will resemble to a disk. Now, if you look from the other direction, it will look like a square. And so how you can achieve 3D imaging with X-rays? So there are a lot of techniques. So you can use tomographic imaging with multiple projection. Of course, it affects the sample because you shine it for a long time, and so long acquisition time, and you cannot do thumb probe time resolve experiment because it's a long time scanning process. So you cannot do single shot ultra fast 3D imaging with this guy. So there are some other single shot 3D technique, but they are really require heavy data treatment, and they can really fail because of noise, rapidly fail. So what we decided is to use a cheap 3D imaging by using two views. It's a stereo imaging using two harmonics beam. I will show you, or two X-ray beams. So the question that we have to ask to ourselves is, can we transpose the concept of computer stereo vision to X-rays? How does it work? So this is our stereo image. So we have this guy with two pictures taken at two different angles. And this is our stereo pair. From these two stereo pair, we can compute what it is called a disparity map. I will not go into the detail, but basically in each pixel, you can assign the position relative to the angle of observation in each pixel. So, and you compute this disparity map, and from them, you send it in kind of an algorithm. You add some 3D point cloud and add some texture. And this is the 3D rendering. So it's already quite spectacular. Of course, it does not, it cannot be compared to 3D technology with gaming and so on, but we want to go to the nanoscale. So we are not interested in gaming for the moment. So this is our sample. This is a silicon nitride membrane with some gold sphere, nanosphere on top of it. So this is a sample that was provided by Henry Chapman. It's an experiment that was done and was published by Henry Chapman in 2006. So, and these are the stereo pairs that he sent to us to get the two angular vision of the sample. And what we did is we have computed the left and right disparity map. And with this, with the point cloud and the 3D rendering, we get the depth information of the objects and a nice 3D rendering of the nanoscale object. So this is the resolution that we obtain, like about 40 nanometer in the XY direction, and you have a bit less resolution in the longitudinal direction. Okay, so this is about what we can do. We have a lot of different imaging modalities. And now what I would like to show you is some perspective for the future. Okay, so most of the talk was, all of the talk was about classical imaging. So there is a standard equation and standard propagation function. Even the phase retrieval thing is not magic. It's just solidly constrained and mathematically can be verified, although there are some problem of convergence and unicity of the solution, but this debate is not closed. It has been solved already. So, but let's move from classical to quantum domain. So, and what we would like to do is to transpose those idea of nanoscale diffractive imaging with short bursts of light and explore the distant action that could be useful with to probe some objects. And the distant action of entangled light, which was contested by Einstein, is now very well verified. We have like Nobel Prize a few weeks ago. It was a month ago, let's say. So basically, I go back to the principle when you want to do an image of an object. So you have a source of light, you have your object, and your detector, okay? So if you want to do quantum imaging, it's not a conventional source, it's a non-classical source of light. So, and which requires either single photon, entangled photon, or squeezed light. And what is important, it is drawn here, is that this this photon pair is strongly entangled with momentum correlation. Now that you have your source of non-classical light, you need also a quantum detector, which will produce single photon detection or a photon coincidence for entangled photon, or for squeezed light, you may want to use homodyne detection. Now this is the experiment that has been published 8 years ago, so by the group of Anton Zellinger. It's a fascinating experiment. I really love it. So this is here your pump laser. You have here the generation of two entangled photons, one being red, shown here, and one being yellow. These are the signal and the idler of the parametric down conversion occurring in this nonlinear crystal. And you have another crystal here doing the same process, and they're all aligned perfectly, interferometrically aligned. So what you want to do with this, what you can do is to put an object here in the path here of the red beam, and then the red beam just go out. And what you do is you detect only the yellow beam. And interestingly, due to the entanglement between the photon pair, information due to spatial momentum, to the momentum correlation, the information is encoded in this photon. And what you will get, so the beam splitter splits the beam in two, so you get these two images, A and B, which are in fact the entangled signature of the momentum that is taken here from the red photon and automatically transfer to the other photon instantaneously, which is really the distant action that was contested by Einstein a century ago. So now if you sum A and B, you get back to the probe here, this yellow probe, which is this one. If you want to recover your object, you just take, for example, A divided by IE plus B, and you get your object here. So it's fascinating. And now we can think about, yeah, what can we do with this and how it is sensitive and what is the resolution? So it is quite sensitive to transparent object, phase objects. So you, for example, here, it's the same apparatus. The camera is here. You have your red arm, idler, signal is here in yellow, in red, the idler. And this is our object, okay? The object is just a phase object on this transparent piece of glass, but it is transparent only at 820 nanometer with a 2 pi shift. So if you put this object in this arm of your interferometer, so between L4 and L4 prime, this is what we would get as an image. You get nothing. You won't see the object because you get a 2 pi shift, and this is what you expect, okay? Now, let's put the same object in the path of L3 prime. And now if you look at the wavelength, we are 15 nanometer, and you get a pi phase shift. So you should see something occurring. And this is what happened, what is revealed in the camera. If you put the object in this area, you see the object and a nice phase shift. But what is interesting is that to measure, this measurement is performed at 820 nanometer, where you're supposed not to see the object. So it's only due to the momentum correlation that you are able to see some phase shifts that were totally invisible at the wavelength you were considering at the beginning. So look at now at the resolution of this guy. So I show here, so entangled pair are generated for no process as parametric down conversions, where you have a pump beam, your crystal, and you generate your photon pair with two different K vectors. So QU is the undetected idler signal, detected one signal, and you have here the waste, and in fact, the momentum correlation depends on the waste. The larger the waste, the larger the momentum correlation. The smaller the waste, so you focus more into your crystal, the lower are the momentum correlation. So you find here the waste decreasing, so from this situation to this situation, and we have our resolution test object. And you see that in this experiment published just in April, so it's a very recent experiment, you see that the contrast and the visibility, how you can really resolve those stripes is totally disappearing when you have a very low momentum correlation. So we know that first, the resolution is strongly related to the momentum correlation, which makes sense, of course. So let's look at the wavelength dependence in terms of resolution of the system. So this is, again, the same test object, and with two different protocols. Either the undetected photon is at mid-infrared wavelength or at short wavelength. And what you see is that even though you detect always at around 800 nanometer, if you use in your protocol a longer wavelength, you have less resolution. Even though you detect at a much sharper wavelength, you cannot reveal this. So it resembles that the resolution is governed mostly by the photon that illuminates the object and not detected. So, and from this article, I would like to read you a few lines. I mean, maybe a lot of you like when people are reading a book. So let me read a little bit of this book. So in a recent experiment, photon pairs with one photon having wavelength in the range of X-ray and the other optical wavelength have been generated. Therefore, it is certainly possible to design an experiment when an object is illuminated by X-ray and the detected photon has optical wavelength. In such an experiment, it will be possible to obtain X-ray resolution using readily available cameras to detect only at optical wavelengths. So this is a paper by Anton Zellinger, and it is a big challenge. But the big challenge is mostly that we don't have efficient source, entangled source of infrared and X-ray. Photon pairs are mostly generated by this parametric down conversion, and they are quite low intensity, but they are simple, cheap, and you can control that in the visible UV range. In the X-ray, the problem is much more complex and much more difficult. Recently, X-ray parametric down conversion has been observed, and in this kind of experimental protocol, they measure some spatial information. Although they did not demonstrate entangled X-ray photons, they were able to demonstrate a quantum-like resolution, quantum-enhanced resolution due to this coincidence detector. But it resembled more like a ghost experiment, ghost imaging experiments. But what we want to do is not to have two X-rays. We want to have infrared and X-ray. And what we want to use is harmonic generation for that. That would generate photons from the higher UV spectral range down to the soft X-ray. So with this, I would like to just, maybe you can refer to the Atto Friday from Maciek Levenstein, and they observe in an experiment together with Paris Salas, the generation of optical Schrödinger cats in the laser matter interaction. So this is the Wigner function, and this is a very strong signature of the quantumness of harmonic generation. For the moment, entangled pairs of harmonic photons have not been observed. What is going to happen soon? This is what I'm working for, aiming for, and we're going to probably succeed. and then perform imaging with either, so this is just a conceptual experiment, so it's a perspective, so this is your harmonic generation. You would beam split and send your soft X-ray onto the sample, and in this unconventional protocol, you will not detect, you just send onto a bucket detector, so you just measure some correlation, and only the infrared or the UV is detected on the spatially resolved detector. And due to the entanglement, hopefully, if we observe it between higher and extreme UV photons, you would be able to resolve this kind of structure with nanometric wavelength, although you do not detect them. So this scheme is inspired from this paper from the group of Scholl Mukamel in the US. So with this, I would like to conclude. I think yeah, it's pretty good in time. So I have shown you that current diffractive imaging enable wavelength limited ultrafast probe. I've shown you that now we have new techniques, a lot of different techniques, not only from our group, but we can achieve broadband current diffractive imaging methods applied to retrieve images from attosecond pulses that have complex broadband structure. And now I would like to draw this perspective. So I arrived at Ecole Polytechnique this year, and we'll continue in this direction of diffractive imaging, but using quantum sources, pure quantum sources, and go into quantum imaging protocol. The technique is at its birth, as I've shown you. There is some controversy also about the resolution, wavelength resolution. So we're not pretty sure that it's going to work. And still, the demonstration from all the groups are in the far field regime and not in the near field quantum diffractive regime that we would like to operate to achieve nanoscale quantum imaging. So in this project at LOA at Ecole Polytechnique, we have David Taylor starting his PhD, Marie-Fraude Poitevaux supporting senior postdoc, and Adam Merdji, who is doing his master in our group. And PhD postdoc positions are available in 23. And we hope that we will reveal quantum X-ray vision and bring this tool to our friend Superman. Okay, with this, I would like to thank you.
So thank you so much. Are there further questions? If you are shy, hang in there, because we are going to stop the transmission soon. And you have the opportunity to ask our speaker questions in an off-record manner. So for those on YouTube, there were quite a few of you today. Thank you so much for joining. Stay safe, have a great weekend. And let's thank also Professor Merdji for this amazing talk. We learned a lot about phases and imaging. And take care of yourselves.
Thank you, Carla.